The beginning of everything, a brief description of the origin and the very early history of the universe. This is a digital sky survey. It might look like a bit of CGI. Think of it more as a 3D map. We've looked at where galaxies are in the sky and measured a lot of their distances, at least for a lot of the galaxies not so far away from us. And using their position on the sky and their distance, we can make a 3D map. And that's what this is. It's a fly-through of a 3D atlas. It tells us that there are A, lots of galaxies out there, but also B, that they're not uniformly spread across the universe. They're clumped together. There are clusters and superclusters, and the galaxies are spread throughout the universe, apparently along filaments. And there are some regions of the universe, so-called voids, that seem to be relatively sparsely populated with galaxies. So the large-scale structure of the universe is this sort of filamentary web structure. And what we're asking in this talk is, can we understand where all this stuff came from? There appear to be billions, possibly trillions of galaxies out there, each of which might contain many hundreds of billions of stars. Where did all of these stars and all of the gas and the dust associated with these galaxies, where did it all come from in the first place? So we've taken a lot of snapshots like this, the Hubble Deep Field, where we've looked out into the universe and we see far more than just the stars in our own galaxy. We see this huge number of galaxies, only a tiny patch of sky. When we scale it up to the whole sky, we deduce that the universe, the observable universe, all of the universe that we can see, seems to contain 1 trillion or so galaxies. But we're asking the question, where did it all come from? We're thinking about the creation of the universe. When did it happen? Well, as best we can tell, it happened about 13.8 billion years ago. We sometimes get the question, how long did it take to make the universe? And one way of answering that is to say, well, it took about 3 minutes to make the universe. And I'll explain why 3 minutes is relevant in due course. Where did it happen? Sometimes a common question, but we have to remember we're talking about the beginning of everything. Therefore, by definition, it happened everywhere. It did not occur at one point in space where you can go and look and say that's where the Big Bang happened. The Big Bang was the start of everything. Why did it evolve the way it did from the very early universe to the universe that we see today? Well, it evolved that way, we believe, because of the laws of physics. And how do we know all this? Same answer, because of the laws of physics. In a sense, we can say the laws of physics are our way of understanding how we came to be in the universe in which we live, based on what we understand as the origin of the universe. So you can think of the laws of physics as being the rules of the game. We are midway through the universe's life. Well, not midway, but we are partway through the universe's life. Its creation is behind us, and who knows where things are heading. That's the source of the next talk about the end of everything. But for the time being, we're asking, how did we get to be here? What are the rules of the game? What are the laws of physics that say if you start with a universe from essentially nothing, you can end up in the universe in which we live? If we were to ask the same of a game of chess, we could ask, how did we end up with the pieces looking like this? From a snapshot of a chess game, can we tell what the rules are that enabled us to get to this position? And the answer is essentially no. There's not enough information in that single snapshot to tell us how to play the game of chess. We might deduce that the pieces appear to be different shapes and they come in 2 different colours. So maybe this is a game between 2 players. But we can't figure out what each piece is able to do just from a snapshot. And similarly, we can't tell how that galaxy ended up looking like that simply from a snapshot of the galaxy. If we were to watch the galaxy for long enough, if we had a video of the galaxy, then over a few billion years, we could watch it evolve and we could figure out how it came to be. But it takes hundreds of millions of years just to rotate once, and it takes billions of years for galaxies to evolve. So we can't determine how things came to be the way they are by looking at a snapshot of a galaxy in much the same way that we can't take the snapshot of a chess game. It would be nice to be able to video a chess game and watch people play. That would tell us what the rules of the game are. But as we've just said, with galaxies, the universe evolves too slowly for that to be a feasible option. We can't sit and wait billions of years to see how it's evolving. But one option with chess is, instead of watching a video of a game being played, we could take a snapshot of 1 million different games, all at different stages from the early game to the late game. Or why stop with 1 million? Why can't we take a picture of 1 billion games of chess, all in process? That would give us an idea, by comparing all of the individual snapshots, that would give us an idea of what the rules must be. Same is true for galaxies. The image of one galaxy doesn't tell us much, but if we were to study thousands or millions, or preferably billions of galaxies, each at a different stage in their evolution, then we would be able to get an idea of how things change. In a deep field image like this, the more distant galaxies, because light has a finite speed and it takes time to reach us, for the more distant galaxies, we're looking at them further back in time. So we're looking at them earlier in their evolution. And so even though it's a single snapshot, this actually gives us information as a function of time, because the more distant galaxies are the galaxies in the early stages of their evolution, and the closer galaxies are a lot further along in their evolution. So it is possible to get an idea of the rules of the game by taking a snapshot like this, or preferably quite a few snapshots of lots of different galaxies. We can get an idea of how the laws of physics work. These days, of course, we not only have a Hubble deep field, we also have a Webb deep field, which can again look at very distant galaxies, and it gives us similar, not quite the same, but it gives us similar information. Because the James Webb Space Telescope is working in the infrared, we're able to see a little further back in time. But when we look at our local part of the universe, what's going on within our galaxy, we might say it's just too complex. There is so much going on in our galaxy. How can we possibly hope to understand the laws of physics? And how can we possibly hope to understand how the laws of physics have allowed structures like this to come into being? But we mustn't confuse the idea of a complex system with one that works with unfathomable rules. For instance, if we look at this particular mathematical collection of pixels, it's called the Mandelbrot set, or this actually is a very tiny fraction of the full Mandelbrot set. It's a mathematical collection of pixels, each of which is coloured according to a particular rule, a mathematical formula. If we were to zoom in, we can zoom in effectively as far as we like, and the pattern never repeats. Some bits look similar. We might look at a particular motif and say, well, this particular structure here that I'm pointing at with the arrow, that looks very similar to another motif and another one and another one. But actually, they never repeat, in much the same way that one star might look very similar to another star, but they're not actually identical. So how complex is the formula that would allow us to construct this picture? Not simply the picture we're looking at, which might comprise perhaps 1 million pixels or so, but what about the entire Mandelbrot set, which contains millions, billions, trillions, quadrillions of pixels? In principle, the number of pixels in the Mandelbrot set is unlimited. So how complex is the formula that allows us to calculate each and every pixel colour? The answer is, that's the formula. The formula itself is very simple. A simple formula, a simple rule, if you like, might result in a very, very complex structure. So even though the universe looks complex, it doesn't mean the laws of physics are beyond our comprehension. And this is a very important point. Complexity is not the same as incomprehensibility. Einstein once said, the most incomprehensible thing about the world, or if you prefer the universe, is that it is comprehensible. There's no particular reason. The universe doesn't owe us anything, and yet it is possible for a certain species on this planet to contemplate the universe and get an understanding of how it's all put together. So there's a flow of thought which helps us understand how the universe has evolved. Within the last 100 years, we've made the observation that galaxies appear to be moving away from each other. And so we come to the conclusion that the universe is expanding, or if we run the clock backwards, the universe used to be a lot smaller. We can also make observations of physics experiments here on Earth, such as banging particles together in the Large Hadron Collider, the LHC. If we bang atoms together, or we bang constituents of atoms together, like protons, we find how atoms and molecules are put together, and hence how the Earth is made, and how we are made, and how the Sun is made. But we have to make some assumptions about the laws of physics. We have to assume that the laws of physics at one place are the same as the laws of physics at another place. In other words, we have to assume that the laws of physics we might deduce in England are the same as the laws of physics that we would deduce if we were in Australia. And indeed, the same as the laws of physics on Alpha Centauri, or the same as the laws of physics in the Andromeda Galaxy, or the same as the laws of physics in any of the superclusters we see when we look out into the universe. We also have to assume that the laws of physics don't change with time. We have to assume the laws of physics today are the same as the laws of physics yesterday, and are the same as the laws of physics will be tomorrow. If that wasn't the case, if the laws of physics changed depending on where you were, or the laws of physics changed from one day to the next, then we would have no chance whatsoever of making sense of the world around us, or the universe around us. If we could not rely on those laws, then all bets are off. Nothing we learn today could possibly be applied tomorrow if the laws keep changing. So we have to assume that the laws of physics are the same everywhere and have always been the same and will always be the same. Otherwise we can make no progress with our understanding. So it is an assumption, but it's a necessary assumption. When we take all of that together, we come to the conclusion that the universe apparently was created in a very hot, dense state 13.8 billion years ago, and it has been expanding and cooling ever since. That is the result of our understanding of the laws of physics and the observations that we make about the universe. But the question we're trying to answer this afternoon is, right, there's an awful lot of stuff out there. We see lots of stars, huge numbers of stars, mixed in with gas and dust. Where did all this matter come from? Everything that we see today, where did it come from in the first place? How far back in time can we go in answering the question, where did it all start? If we're trying to answer the question about the beginning of everything, how close back to the beginning of everything can we go? How long before we say we don't really know whether we understand the laws of physics well enough to be sure that we know what we're talking about? Can we go back to the first year of the 13.8 billion year history of the universe? Yes, we can go back to the first year. What about the first day? Yes. What about the first hour? Yes. What about the first minute? Yes. What about the first second of this 13.8 billion year history? Yes. What about the first millisecond? Yes. What about the first microsecond? Yes. What about the first nanosecond? Yes. What about the first picosecond, the first trillionth of a second after what we believe to be the instant of creation? No. At this point, we have to say we don't really know whether or not at this point we know the laws of physics as we understand them today are held. Before the first picosecond, we are on somewhat shaky ground. From 1 picosecond onwards to the present day and beyond, we think we've got a relatively good understanding of how the universe evolved, how it came to look like it does, and what it will look like in the future. So there's a watershed at 1 picosecond, 1/1,000,000th of a second, and I'll explain in due course why the watershed exists at that particular time. So that was a rather long introduction to what I'm talking about this afternoon. I'm going to start on the next slide with a few basic ideas which we'll need to make sense of what's coming in the subsequent slides. And then I'll be describing what happened in the first fraction of a second, what happened in the first few seconds, what happened in the first few minutes, and then changing gear slightly and going fast forward and asking what happened 380,000 years later. Again, there's a good reason for that particular number. And then change gear again and say, right, how do we end up with the universe that we see today, 13.8 billion years later? So we're going to start with a few basic ideas. Some of these I'm sure you're aware of, some of them maybe not. So let's start with, we are made of atoms. I hope that comes as no surprise to anybody in the audience. We know what atoms are made of. Atoms are made of a positively charged nucleus surrounded by negatively charged electrons. And we've known for quite a while that we can take atoms and we can split them into precisely that, positively charged nucleus and negatively charged electrons. So atoms are not what we call fundamental. They are made of other things. And with enough energy, we can split atoms and separate the electrons from the nucleus. Electrons, as far as we know, are fundamental. They are not made of anything. They just are. In other words, we can't take an electron, cut it in half, have a look inside and see what it's made of. It's not made of anything. However, a nucleus is made of something. It's not a fundamental particle. It is a so-called composite particle made of something else. And given enough energy, we can split a nucleus and find that it's made of other things. A nucleus of an atom is made of some combination of particles that we call protons and neutrons. And neither protons nor neutrons are fundamental because, again, they are made of something else. When we look inside, we find that they are made of quarks. Now, I'm not going to describe why we call them quarks. I'm just going to use these labels of protons, neutrons, and quarks as being types of particle. What's important is, are they fundamental? Are they made of anything? Or are they fundamental and not made of anything? Or are they composite particles that are made of something else? So quarks make up protons and neutrons, as it happens. And if we take those combinations of protons and neutrons and combine them with electrons, we get atoms. And when we put atoms together, we get molecules. And when we put molecules together, we get us and pretty much everything else we see in the world around us. But as I was describing this sort of Russian doll idea of atoms are made of smaller stuff, nuclei are made of smaller stuff, protons are made of smaller stuff, there's an implicit energy scale because it takes more and more energy to separate atoms and then separate nuclei and then separate protons into their constituents. So there's an implicit energy scale going from low energy at the top to high energy at the bottom. But remember our deduction about the universe expanding and cooling. As far as a physicist is concerned, high energy and high temperature are essentially the same thing. Temperature is just a way of measuring how much energy the various constituents have. So low energy and high energy you can think of as cold and hot. And if the universe started out hot and is expanding and cooling, then there's an implicit time arrow running from the bottom to the top. In other words, the universe was built from the bottom up. If we can imagine a universe full of fundamental particles like quarks, those quarks can't get together to make a proton until the universe is cold enough for that to happen. If we try and make quarks into a proton whilst the universe is still very hot, it's so hot the proton will fall apart and we'll be back to 3 quarks again. Similarly, we have to wait until the universe gets cold enough for protons and neutrons to get together and make a nucleus. If we try and put protons and neutrons together to make a nucleus before the universe has cooled enough, then there's so much energy there, again, the nucleus will fall apart and separate into its constituent protons and neutrons. And again, we have to wait even longer for the universe to cool to the point where a nucleus and electrons can get together to make atoms. So there's this time process. We can build from the bottom up. Quarks to make protons and neutrons to make nuclei, nuclei and electrons to make atoms. And it must happen in that sequence because the universe is slowly cooling down, allowing us to go through these various layers, if you like, of structure. So that's the idea that will help us make sense of the next few slides. We start at time t equals 0 and ask what happened at the instant of the creation of the universe. And we have to admit that science cannot provide a definitive answer. We only really know what's happening from 1 picosecond after t equals 0. So at this instant, we don't know what happened. There is speculation, there are hypotheses, but we can't test our ideas because we can't reproduce the energies involved in any earthbound experiment. Perhaps it was a quantum fluctuation in which energy is borrowed from nothing. Now, the idea of borrowing energy, or indeed matter, from nothing sounds really weird. Surely you can't get something for nothing. Well, yes, you can, according to quantum theory. And yes, it sounds weird, but then quantum theory and quantum mechanics, which describes how quantum theory works, well, yeah, quantum mechanics is weird, and that's the subject of a completely different talk. And if you're allowed to borrow energy from nothing, and if you borrow energy, E equals mc squared, so if you borrow energy, you can make matter. If you borrow matter, you can make energy. That means effectively you can borrow from nothing and make as much stuff as you like. Within limits, how big can this quantum fluctuation be? Well, it turns out, according to quantum theory, the product, the multiplication of energy times the time that you've borrowed that energy does have an upper limit. It's like borrowing from the bank. You can borrow a lot of money for a short time or a little bit of money for a long time, and you'll end up paying back the same amount of interest. So in this case, you can borrow a lot of energy for a short time or vice versa. So perhaps a key question is, well, how much energy do we need to borrow to make a universe? What is the total energy budget of the universe? It's a rather tricky thing to calculate, but if you work out how much matter is out there and say, well, E equals mc squared, we can get the energy equivalent of all of that matter. And we look at all the gravitational energy. Well, the matter energy is positive and the gravitational energy is negative, and when you add it all up, it looks like the answer might be 0. If the answer is 0, the total energy we need to borrow is 0, and so the time that we have to pay back the loan, as it were, before the universe notices, well, maybe that's infinite. I know that sounds like a bit of a fudge, but most arguments in quantum mechanics sound like a bit of a fudge. The answer, remember, is this is hypothetical. This is speculation. We do not know. Let's move forward a little bit in time. Let's move forward to the time of 0.000. You can count the zeros yourself. At the unimaginably short time of 10 to the minus 35 seconds after creation, the universe has expanded. The observable universe has expanded until it's about the size of a golf ball. In other words, the observable universe at the moment is approximately 100 billion light years in diameter. And we can imagine all of the galaxies and all of the stars and all of the gas and all of the dust inside that 100 billion light year sphere. If the universe is expanding, then everything used to be a lot closer together. Everything that we currently see inside the observable universe used to be separated not by billions of light years, but by centimeters. That's what I mean by the observable universe was about the size of a golf ball. Just like the golf ball, the universe was not perfectly smooth at this point. Now, a golf ball has dimples in the surface. This is only an analogy, but basically the universe back at this time period must have had small variations in its density and in its temperature. In other words, it wasn't the same temperature and the same density of whatever stuff was in there. It wasn't the same density and temperature everywhere. There were small variations, and I use the dimples in the golf ball just as an analogy. Eventually, over the course of time, when the universe is much, much bigger, these small variations in density and temperature, these dimples, will give rise to the density variations that we see in the universe. In other words, we see galaxies over there and another supercluster of galaxies over there, and we see some areas that are relatively low density. These dimples eventually give rise to the structure, the large-scale structure that we see in the universe. We now move forward to 1 picosecond after the Big Bang, 10 to the minus 12 seconds, 1/1,000,000th of a second. The universe has now expanded from the size of a golf ball to something about the size of the solar system. Of course, the solar system doesn't exist yet, but that's just a reasonable way of judging the scale. This happens in 1/1,000,000th of a second. It goes from something that's tiny to something that's many light hours in diameter. So it has expanded much, 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 much faster than the speed of light. That's allowable according to our understanding of the rules of the game, the laws of physics. The universe can expand at any speed it wants to, and it seems that it used to expand really fast, and it has been slowing down for many, many billions of years. Regarding the speed of light, it's only the passage of objects through space that is limited by the speed of light, not the rate at which space itself can expand. The temperature after 1/1,000,000th of a second has fallen to 10 to the 15 Kelvin, and the energy of each of the constituents, if we borrowed energy, we could make as much mass as we like with that energy. I'm assuming that the mass we make is a whole load of quarks. It won't necessarily be quarks, it could be a whole load of quarks and electrons and other rather exotic particles. But just for convenience, I'm simply going to call it a quark soup, simply for brevity, rather than calling it a soup of particles which might include quarks and electrons and other exotic particles. So each of the constituents of the quark soup at this particular temperature is approximately equal to the energy that we can generate in the Large Hadron Collider. And that is why we say that we understand things from this point onwards. We can test our ideas because the energy of the particles involved from this point onwards are comparable to the sort of energies that we can create in a particle accelerator like the Large Hadron Collider. If we can test our ideas, then we get a good idea of whether our ideas are right or wrong. Prior to this point, it was speculation. From this point onwards, the ideas are testable. We can have an hypothesis, we can do an experiment, we can see if we're right or not. If we borrowed energy, we can make matter. And energy and matter are continually exchanging back and forth. Every time we use energy to make matter, we actually make a particle or more than one particle of matter, and we make the equivalent antimatter as well. To start with, exactly equal amounts. Every time we generate or create an electron, we also create an antimatter equivalent of that electron, a so-called anti-electron or a positron. If we make a quark, we make an anti-quark as well. Every time we make matter, we make some equivalent amount of antimatter. I can demonstrate that graphically by assuming that energy, I don't know how to draw energy, so I'm just going to put a big capital E to mean a certain amount of energy can be used to make a particle of matter and a particle of antimatter. Which ones does it make? It doesn't actually matter, if you'll excuse the pun. Energy can be used to make something and anti-something, probably not a tangerine and an anti-tangerine, but the point is it doesn't matter. It could be an electron and an anti-electron. It could be a quark and an anti-quark. It could be something exotic and an anti-equivalent of that exotic particle. The matter and antimatter particles are going to annihilate with each other, and that produces energy. And that energy can be used to make another particle and antiparticle. Not necessarily the same ones again. It could make something completely different. Probably not a hot dog and an anti-hot dog. It's going to make another matter particle and its antimatter equivalent. Backwards and forwards, backwards and forwards. Energy changes into matter, matter changes into energy. Back and forth, back and forth. Somehow, via a mechanism we don't really understand, matter gained a very small excess over antimatter. In other words, we can imagine a whole load of matter being made and a slightly different amount of antimatter. I've shown the excess here as being about 10% or so. It wasn't that big. The difference between how much matter was made and how much antimatter was made wasn't 1 part in 10, it was more like 1 part in a billion. But I didn't have that many graphics to deal with here. So when the matter and antimatter annihilate with each other to make energy, we get a whole load of energy, mainly in the form of radiation, floating around the universe, and there's a tiny bit of matter left over on the right-hand side there that hasn't got an equivalent antimatter to annihilate with. So we end up with a universe which is full of radiation, or light if you prefer, and a tiny, tiny amount of matter. But that matter is everything that we can see. Every star in every galaxy, every atom of gas, every atom of dust in the universe is that tiny bit of matter that's left over on the right-hand side, including, of course, you and me and the Earth and the Sun and the Milky Way galaxy. This would imply that if it was 1 part in a billion left over because of that asymmetry between matter and antimatter production, there ought to be something like 1 billion photons of light for every particle that's floating around in the universe. And that is indeed what we see when we try and do that measurement. We're now moving forward to 1 millisecond after the Big Bang. Matter and antimatter are continuing to pop into and out of existence. Now eventually we can make protons and neutrons out of constituent quarks. In other words, quarks are being made all the time, and whenever we have 3 quarks together, a particular combination of quarks, as indicated on the left-hand side, that's what we call a proton. And that can change because quarks, remember, can change into energy and energy can change into quarks. Then a particular combination of quarks, I'm not going to explain why we label them U and D. I'm not going to explain why we draw them in 3 different colours. Let's just accept that that particular combination of quarks shown on the left is a bag of quarks that we call a proton. And the particular bag of quarks on the right is a different combination, and we call that combination a neutron. And quarks are changing into energy, and energy are changing into quarks, back and forth, which means protons are changing into neutrons, and neutrons are changing into protons, back and forth, back and forth. After a few seconds or so, the universe has now cooled to only about 1 billion Kelvin. And because it's cooled down to that temperature, it's now effectively too cold for this exchange of protons into neutrons to readily swap back and forth and back and forth. Now, protons are a little bit lighter than neutrons. They are now, and we believe they were then. How do we know protons are lighter than neutrons? Well, basically we measure them in a laboratory and we find that protons are lighter by about 1 part in 1,000. So if there's a difference in mass between protons and neutrons, and fundamentally we think protons and neutrons are no different in the distant past as they are today, and again, they will be no different in the future. If protons are lighter than neutrons, we find that protons should outnumber neutrons, and it turns out the ratio at a temperature of 1 billion Kelvin, the ratio should be about 75 to 25. So I'm showing on the right-hand side, red circles represent protons and blue circles represent neutrons. And I'm just showing a representative set of 16 particles to show you the ratio is 75 to 25. In other words, 2, 4, 6, 8, 10 versus 2, 4, 6, 8, 10, 12 versus the 4 of the neutrons. So why is it that we get more protons than neutrons? Because nature always favours the lower energy, or in this case, the lower mass. It's like saying the universe is able to make as many protons and neutrons as it likes, but protons are lower mass. If protons are lighter, well, they're easier to make. And so if the universe can make lots of protons and lots of neutrons, if protons are a little bit lighter, it turns out they're easier to make, and we would expect that particular ratio for the number of protons and neutrons when the temperature of the universe has fallen to about 1 billion Kelvin, which it will do after a second or two after the Big Bang. After a few minutes, about 100 seconds or 200 seconds, something like that, we know that neutrons are unstable and will change or decay, to use the physics term, into protons. Again, how do we know that? Because we can do laboratory experiments now and we determine that neutrons are unstable, and in isolation, if they're not in the nucleus of an atom, they will change from neutrons into protons. And if that's what they do now, we believe that's what they would have done 13.8 billion years ago. It takes about a quarter of an hour or so for a neutron to change into a proton. So some of those protons will now get a few extra because some of the neutrons that we said before have changed into protons. So instead of the ratio being 75 to 25, remember I had 16 representative particles here, of which 12 were red and 4 were blue. Now 2 of the blues have changed to red, because we can calculate that after a few minutes it would be possible for some of those neutrons to change into protons. So we now have that ratio, 14 protons to 2 neutrons. Once the universe has cooled to about 100 million Kelvin, it is possible for the protons and the neutrons to get together. Prior to this point, the universe was so hot that when protons and neutrons try and get together, they have so much energy they simply don't stick, they fly apart. But from this point onwards, after a few minutes or so, it is possible for protons and neutrons to get together and stick together. What they really want to do is to form the most stable structure they can, and it just so happens the most stable structure they can make is made of 2 protons and 2 neutrons, 2 reds and 2 blues. And so that's what happens. But of course, there's only 2 blues for every 14 reds. So what that means is 12 reds have to stay bachelors, while 2 of the reds pair up with 2 of the blues. 2 protons pair up with 2 neutrons to make a so-called alpha particle, this particle on the right-hand side, which is also the nucleus of a helium atom. And what we're left with is 12 bachelor protons, which are the nuclei of hydrogen atoms. And from this point onwards, the universe is too cold to change that. So after 3 minutes, the relative abundance of hydrogen and helium in the universe is determined. It is effectively fixed at this point. When we look out into the universe and ask ourselves, of all the gas that's out there, how much is hydrogen and how much is helium? The prediction here is that it should be 3/4 hydrogen by mass and 1/4 helium. And that is indeed what we see. Now, yes, of course, stars are slowly fusing hydrogen into helium. So in the cores of stars, hydrogen is being used up and helium is being made. But if we look at the gas in general, all the gas that hasn't yet been used in stars, we get exactly, or to within experimental error, we get what we would expect from this Big Bang theory, that we have 3/4 hydrogen and 1/4 helium. Because this is predicted by Big Bang theory, and because that is what we actually see as observational evidence, that's one of the reasons why we think Big Bang theory is correct. We're now going to fast forward 380,000 years. because nothing much of any consequence happens for the next third of a million years or so. The universe continues to expand and the universe continues to cool. Eventually, the universe reaches a temperature of about 3000 Kelvin. Why is that particular number relevant? Well, because that's the temperature at which nuclei can hang on to electrons. A nucleus can hang on to an electron as long as the temperature is low enough. If you take an atom with a nucleus and electrons, if its temperature is way above 3000 Kelvin, the atom breaks down. In other words, the electrons are lost. But if the universe is cooler than about 3000 Kelvin, it's possible for nuclei to hang on to the electrons that are also floating around in the soup of particles. And so from this point onwards, it is possible for atoms to exist. Not simply nuclei and separately electrons floating around, but the nuclei can hang on to the electrons and make atoms. So instead of the universe existing as a plasma, now the universe exists as atoms, neutrally charged atoms, positive nucleus, negative electrons, no overall charge. For the first time in the history of the universe, after 380,000 years, the universe becomes transparent to light. Before this, the light was simply rattling around, getting continually bounced around in the plasma. But from this point onwards, the light is free to fly across the universe. And we see that light today. Originally at 3000 Kelvin, well, objects would have been white hot, and so there would be a lot of visible and ultraviolet light at that point in the universe. We do see that light, but since then the universe has expanded something like 1,000-fold in terms of its size, and the wavelengths of the visible and ultraviolet light have been stretched out from something only a fraction of a micron or so. It's been stretched out 1,000-fold, so instead of the wavelengths being microns, the wavelengths are now more like millimeters. And that particular light is microwaves. And that is precisely what the cosmic microwave background is. When we look out into the universe, we see microwaves coming from all directions in the sky. This is an all-sky map that's been unwrapped in order to show us the whole sky at once. So we don't see it as a glow in visible light, we see it as a glow in microwaves, because the universe has expanded since this point in time. It is essentially the same in all directions, except if we look in real detail, we find that these fluctuations, as indicated by the scale here, anything in red is slightly higher intensity microwaves, anything in blue is slightly lower. It's only a small variation because it's essentially the same in all directions, but there are small variations, less than a part in 1,000, between different points in the sky. Remember the cosmic golf ball? There were dimples. There were small variations in density, small variations in temperature in the very early universe. And those small variations in density and temperature have effectively imprinted themselves on the microwave background. So in a sense, we're looking at the dimples in the golf ball from that very early universe. That's why it's rather important to study the cosmic microwave background. It's not the same in all directions, and the small variations tell us about the dimples in the golf ball, and that helps us understand how the galaxies ended up the way they are. The small variations in density were exaggerated by gravity over billions of years, and the dense parts became even denser and the low density became even lower density, and that gave us galaxies and clusters of galaxies and superclusters of galaxies. So satellites are being used to study the cosmic microwave background. The greater precision with which we study the background, the more detail we find about that very early universe. We can see a simulation to give us an idea of how the variations, the dimples in the golf ball, if you like, can give rise to variations in the structure of the universe we see today. If we take a simulation in a computer, we're taking a large cube, filling it with material, but we're not filling it completely uniformly with matter. We're putting in a small variation. You can see the shade of blue represents the density. Some bits of this square are looking a little brighter blue than others. That shows you that we've got some variation in density and temperature across this square, which represents part of a cube of space. And we're now going to run this simulation forward over a few billion years and let gravity do its stuff. What happens to these small variations as we let gravity work? Let's run the simulation. Some parts are getting even brighter, even denser, and some parts are getting darker, even less dense. And wherever we get a really bright concentration of matter, that's where galaxies and clusters of galaxies are going to form. You can see we're starting to form a filamentary structure, a cosmic web. Remember the fly-through of the 3D atlas that we started with? When we look at where the galaxies are in the universe, we find they're not uniformly distributed. There seem to be clusters and voids and filaments in terms of lines of galaxies running throughout the universe. So we can understand this cosmic web structure by running simulations in computers where we start with a few dimples in the very early universe, and gravity gives rise to the density of structures that we actually see today. And it's simulations like this that again give us some confidence that understanding the evolution from the very early universe to the present day, if the simulations give us structures that we do see in the universe, that gives us some confidence that we're doing the simulations right, and our initial understanding of the initial conditions must be at least approximately right. If we look at what's going on, this is just a little map, if you like, a cartoon map of what's going on around the Milky Way. The Milky Way is surrounded by a few minor galaxies, and over there on the right-hand side, that's the Andromeda Galaxy. So this is the local group, very much our immediate neighbourhood. If we change scale and look further afield, our local group is now in the centre of this map, and we see a Virgo cluster out on the right and a Fornax cluster on the bottom left. And we perhaps note that these clusters are not distributed randomly. They appear to be in a sort of curvy line. There's a filament running from bottom left to top right of individual galaxies and galaxy clusters forming a filament of the large-scale structure of the universe. And that's more evident if we change scales once again and go even further out into the universe. We now see the Virgo supercluster in the middle there, and again we see lots of filaments and we see lots of structure. And on the right-hand side, we notice there are some regions that appear to be almost devoid of any galaxies at all. Again, this is all a manifestation of the fact that we started with a golf ball with dimples, variations in density. Some have become much more dense and formed galaxies, and some have become less dense and formed voids where there appear to be very few galaxies at all. So we do have some understanding of how the early universe came to look like the universe we see around us today. What if we fast forward now for the next 13.8 billion years to the present day? If we can understand that it takes 3 minutes to make all the hydrogen in the universe, then we pretty much have a basic understanding of, well, almost everything. If we understand where the hydrogen comes from, then we understand how we can have stars that form galaxies. And we understand the individual processes within those stars, fusing hydrogen, giving out energy as hydrogen is fused into helium and then heavier elements. And if we can understand galaxies and stars, then in principle we can understand planets, and we can understand trees and mountains and snowflakes and rainbows and cats and okay, maybe not cats. I'm not sure we'll ever understand cats, but we can understand most aspects of the way the universe is put together. Yes, of course, there are lots of details to be worked out. But if we understand that it takes 3 minutes to make all the hydrogen in the universe, you could say that everything flows from that one observation or that one piece of understanding. So we can think of a very odd timeline as a graphical summary, if you like, from ridiculously short times on the left to very long times on the right. We borrow energy from nothing and we make matter, and the universe expands until it's the size of a golf ball, we think. This is just hypothetical. And if we borrow energy, we can make matter and antimatter. Not just quarks, but also electrons and loads of other particles, but I've just called it a quark soup for brevity. After a little bit of time, the universe cools enough for those quarks to get together into bags of 3 quarks, which we call protons and neutrons. A little while later, the universe has cooled enough for those protons and neutrons to get together to form the nuclei of helium, and any protons that are left over are what we call the nuclei of hydrogen. After 380,000 years, those nuclei can grab hold of electrons to make neutral atoms. For the first time, the universe becomes transparent. The light is released to fly across the universe, and we see that light in all directions as microwaves, because the universe is now 1,000 times bigger than it was back in those days. After the light is released as the cosmic microwave background that we see today, it takes a little while for stars to form. We have a period called the Dark Ages. How long is it after the first million years or so before the first stars are made and the first galaxies are formed? Well, we don't really know. That's why the James Webb Space Telescope is currently looking back in time as far as it can go to try and figure out when were the first stars made, when were the first galaxies put together. Was it 100 million years? Was it 500 million years? We figured it was probably a fraction of a billion years, but it looks like those first stars were made rather earlier than we first appreciated. But we know that those first stars were born, and galaxies have been evolving for the billions of years over this 13.8 billion year timetable until we see the galaxies around us today. So there's a brief way of looking at the entire timeline of the universe. I have to admit there are still some gaps in our understanding. The jigsaw is not really complete. We have some fairly fundamental questions to answer. Why did matter win over antimatter? It appears to have happened, but we don't know what caused the asymmetry in the first place. Why didn't the universe just make equal amounts of matter and antimatter? If it had done that, all of the matter would have annihilated with the antimatter, and we would be in a universe full of radiation and nothing else. In other words, when I say we, I don't mean us, because there would be no matter in the universe at all, only light, and there would be no stars, no planets, no life. So it's just as well there was an asymmetry, but we don't understand its cause. And I've been rather careful to talk about everything that we can see in the observable universe, all of the stars we can see, all the galaxies, all the gas, all the dust. But there's a whole load of matter that we can't see. We think dark matter is out there because of the effect it's having on the way stars are moving in galaxies, for instance, rotating at speeds which look wrong according to our understanding of how much luminous matter is out there. So it looks like the universe is also full of something that is not luminous, so-called dark matter. And more recently still, it looks like there's something else out there which is causing the expansion of the universe not to slow down, but to accelerate. For the first few billion years of the universe, the expansion was slowing down. The original acceleration was very fast, and then over billions of years it slowed down. But now it looks like it's starting to accelerate again, and we don't understand why. We've given the label dark energy to this phenomena, but just because it has a label doesn't mean we understand what it is. So the talk is entitled The Beginning of Everything, but I've been very careful to try and make it clear that everything means everything that we can see. But everything that we can see only accounts for about 5% of what we think is out there. The other 95% is still a bit of a mystery. But as they say, that's another story. Thank you for listening.